Hello, welcome to another problem session. Today we have an interesting projectile motion problem. So you have done problems like this where you shoot some projectile and comes back. But you've done assuming like all the time the force of gravity is mg and g constant. So that's not the case now. We want to use actual force of gravity from Earth. And so we're still shooting at a angle theta 0 with a v0, and it's going to go and it's going to land somewhere. And we want to know what's the highest point it's going to go before it's turning back towards Earth. Okay. There is you probably already know that this thing is a part of an ellipse. If this path continued, then this will be part of an ellipse with this center of the Earth at one of the focus, and it's going to be. It's like that, right? So this is apogee, and this is perigee of this elliptical motion. So you can use the projectile, the elliptical motion of the trajectory, and you can actually find this distance from the eccentricity and things like that. So you can always do that. So just to recall, for this two-body motion, you have a mass of Earth, and this is mass of this projectile, and we make a mu. I convert this two-body problem to one-body problem. Mu m over m plus m, which is close to a small mass, and mu kind of captures the motion of this smaller mass. And becomes a one-body problem. And if you look at from here, say at time t, it's here. If this distance is r and this angle is theta, then you have r at t equals to r0, which is constant, 1 minus epsilon cosine theta at time t. Then r0 and epsilon are, we've gone over this a couple of times now. R0 is, and this can be related to angular momentum, and this will be related to energy and angular momentum. And you can look up the formulas. Another way to look at it is angular momentum vector is mu r cross v at any time, and this is conserved, and energy is half mv square minus actually mu v square g m over r for the mu particle, but this remains m original potential energy. This is speed, and so you can write down the radial and the angular, and so half mu radial is speed square plus half mu. You can write this as mu r square theta dot square for for angular, which is g m over r, and this you can write down as a angular momentum 1 over 2 mu L square over R square minus G M over R. And in many, in this whole thing, is a function of r, and it's called effective potential energy, U effective. Okay, so that's so much for theory. Okay, so how are you going to solve this problem? There's sufficient for information now for you to actually use conservation laws into this problem and try to solve this yourself, and see if you can pause this video and see if you can solve this yourself, and then I will start. Okay, so how I'm going to solve it? Well, I'm going to look at this point, call it some point. This point I'm calling A. Let's call this point B. So we'll say angular momentum at A equals to angular momentum at B. That's one equation. And second equation will be energy at A equals to energy at B. And that should be sufficient to solve this problem. These two will be okay. So now LA is magnitude. So if you look at this, at this point the R vector, at this point this is the R vector whose magnitude is the radius of the earth, and V0 vector is that way. So you can cross product. To make the cross product, you need that's the lever arm you need, right? So if you look at R cross V, so if this is, if you went out there and made this R vector, and so you need this angle. That angle is you can see that angle is going to be 90 degrees minus theta. So this is 90 degrees minus theta. So cross product, if you this magnitude of this times magnitude of this times sine theta, mu r v sine of the angle between r and v. So at this point, sine of that angle is sine of this angle, which is cosine of that angle. So this just becomes mu r is the radius of the earth at this time, v is the v0 at this time, and I mean this is b, and I'm going to do a later, okay, at point b, and then I have a cosine of theta 0. How about this guy? This guy is just it's LA, and I will just leave it like this right now because I don't need to find this. I don't have information for V, and so I actually don't, I only know the V is pointed into angle direction. So V is theta dot at this point in that direction. But other than that, we don't know. If you want to know that, that's going to be RE plus, and that's going to be 90 degree. So this with this sine of 90 degrees will be 1, and so that's just going to be equal to R mu RE plus the height we have to go times theta dot. And from there I can actually get the theta dot, or I can get LA. So these are equal to each other, and you can see the mu is cancels out and things like that. So I'm just going to leave it like this for now. I'm just going to leave it like that. So this is equation 1. And equation 2, for in terms of EB is very easy to get, right? I have a potential energy at this point plus kinetic energy. The speed is given, so I get half mu v0 square. So it's given in terms like that. Entire speed is given, not just radial and angular. And then radius of the earth, that's how far it is. So minus gmm of the radius of the earth. So that was easy to get. On the other side, what do we have? We have it's at that distance and it's going at this angle. So, but there's no r dot is 0. So this part is 0. So I can just use this form, and so this is equal to 1 over 2 mu L at a square over r plus height square. So now LA, this whole thing is LA, and this LA is equal to that, so I can actually write the, I forgot to write the potential energy, minus GMM R earth plus H. So that's, this together is the energy, and I can see that this LA, I can put in here this expression for that LA, and so I will have a big expression. Let me clean this up so I can have more space. Okay, so now those are two expressions I got, one from angular momentum conservation and one for energy conservation. You can see now that if I put it in here, I'm going to so this will become this whole thing is square in here, and this mu will cancel this mu, and the thing I'm trying to solve is right here and here, and this is in the square. So I think it's a good idea to convert this into something algebraic. Okay, so this looks like, if I call this whole thing, let's call 1 over RE plus H, let's call that X, then you have this whole bunch of stuff, AX square, and this is minus BX, this whole thing, and then you can bring this on the right side, you can call that C. So you might call it BX plus C equal to 0, with it A is equal to mu RE square V0 square cosine square theta 0 over 2. So that's A. And what's the B? And B is minus G mm, that's B. And what's C? And C is this whole thing came on the other side, half mu V0 square. So all of these are known. If I this is 2, not a square down there. So all of these are known once we know the masses and things like that. But you can also see that if I do m close to mu or mu close to m, then I can actually get rid of this mu, this m, this mu, this m. So we can get rid of these m's here and the mu's. So I don't need to give in the mass of the satellite, right? And then you can clearly solve this for x, and x is equal to 1 over RE plus H, and so you can see H equals to 1 over x and minus RE. So that's the final answer. I can go through this. Now it says I don't need to do numerical, and this is just a very messy answer. That's where the part B comes in. With this choice and this angle given, a lot of these numbers will simplify. and that's what I'm going to do next. Okay, so let's do the b, so where I can simplify lots of these numbers. All right. Okay, looking at this this way of writing for v0, given v0 rather than numerical value, suggests that we should think about gm0, gm over re, gm mass of the earth over re. So m is earth, right? So over here, this part is going to be very easy to write down. It's going to be just square both sides. So this is going to be 4v0 square. So this will turn into 4v0 square. This one here, I will have to do divide by re and multiply by re. So over here, this is a little bit more complicated. So let's write the first one down. So 1 over 2, we have a re square v0 square cosine square theta over, let's call this thing y square, and minus what we got at re, and this combination is 4v0 square re plus h. We're going to call it y now. And on the other side, we have a half v0 square minus 4v0 square. So you can see the v0 kind of goes away from every term. That's very nice. So v0 goes away from each term. And so this is minus 3.5, which is minus 7 over 2. And it seems like this cosine theta is 0. Now, with 45 degrees, that's 1 over square 2, this becomes half. And instead of solving for, writing down the answer for re, let's absorb that. Let's call it let's call it z square, and z equals to y over re, and y was re plus h. So you can see I can, if I get z, I just multiply by re, and so it's working out nice. Over here also is z. So now we have pretty simple formula here: 1 over 4z square minus 4 over z equals to minus 7 over 2. Let's multiply by z square everywhere. So I get a 1 over 4 minus 4z is minus 7 over 2 z square, and multiplied by 2. So bring it on this side. Maybe I'll just leave it like 7 over 2 z square minus 4z plus 1 over 4. So I hope I didn't make a mistake. I really didn't work it out earlier. I just working out for the first time. So the z will be 1 over 2a, 1 over 2 times 7 over 2, minus b, which is 4, plus or minus the square root over 16 minus 4 times 7 over 2 times 1 over 4. Okay, so this 4 cancels this 4, and so this is nasty. So we got z, and you'll have to choose between the two values and then convert that into y from the z. So y equals to re z, and h equals to y minus re. So y minus re makes it so z minus 1 re. So now we have the z, and then you can complete this. Okay, so rather than complete this whole calculation, you can see the process by which I will go. And this numerical values given actually simplifies this thing. This problem is a modification of the problem, a similar problem I believe it's in Kleppner and Co. I think I've seen this problem, a similar problem there. Okay, just a reminder, if you like this kind of videos, let me know what problems I can solve here. Don't forget to subscribe to this channel. Whenever I upload, you get a reminder, I believe, if you subscribe to this channel. This is a good problem to practice, because the next problem I'm going to do will be something like this. Okay, I'll just set it up for you. The next problem I'll do will be like so this problem says something very interesting. No matter whatever it's going to hit, even if you're at very high speed, it's going to come around and hit. It's part of the, as long as you're shooting within this angle, it's going to come hit the earth, right? So how do I make something go in a different orbit? Suppose I want some projectile to go in this orbit. What will I have to do? So you see over here, this kind of intersect, right? So suppose I shoot it. Originally I shoot it. Let me give different color. Originally I shoot it at this angle, and it would have gone out there, and maybe come back and hit over here. Maybe I shoot it with this, but when I get to that point, I'm going in that direction if I don't do anything. But if I apply a force in that direction, then I can actually change its trajectory. I can change its trajectory to this direction, right? I can change its trajectory to that direction. So this is the V in V for maybe original path 1. Original path 1. But I want to go into path 2. So this for path 2, this is path 1, path 2. So I need to apply a force or an impulse. There's no outside force to apply. So the satellite or aircraft or spacecraft that you have, it has to actually push a rocket in some direction, so that velocity this way has to change direction to this way, and consistent with the energy conservation for this orbit. So I want this called orbit hopping or orbit changing or orbit correction, and I want to try to make a problem like this and address that problem in the next video. Okay, talk to you later. Bye.